Thank you. I'm Yannick BLEU. I'm in a postdoc. I started just a postdoc 2 months ago. So here I'm going to show you just to present you the project in which I'm working. So it's a low temperature vanadium dioxide thin film for protection of electronic and optical devices. So I'm working under the supervision of Christophe Donnet with a lot of collaboration, as you can see here, in the laboratory Hubert Curien, in École des Mines, and with HF. So the technological context is that in electronic circuits and optical devices, there is a need of protection against, for example, in electronic circuits, against the passive attack and active attack. And this can be controlled thermally by thermally activated control. And actually, this can be done using a thin film that's how to say, a thin film that's ruled at low temperature. So here the idea is to use the low temperature thermochromic vanadium dioxide thin film to then make radiation blocking random for electronic circuit, and also make a device that can be thermally activated at variable temperature in optics, like switch or optical filter. So this thermochromic vanadium dioxide actually is interesting because it has a reversible insulator metal transition at 68 degrees Celsius. And the idea of this project is then to reduce actually this temperature to go close to the room temperature. However, this material is a bit complex because it can have a lot of form. So it has up to 7 polyforms. However, here I'm going to focus on these 2 stable forms. And the idea is that this material has 2 phase transition. So there is electronic transition going from semiconductor to metal, semiconductor below the 68 degrees Celsius, and metallic to above the 68 degrees Celsius. And this transition is governed by electron-electron interaction. And also it exhibits structural phase transition. So below the 68 degrees Celsius, it's monoclinic phase, and above it's reticle phase. And this is also governed by the electron lattice interaction. Just to show you some example of the transition. Okay, here it's a transmittance against the temperature. And this transition actually is accompanied by the hysteresis because it's reversible transition. And this is for resistivity, just to show you an example. And there are some parameters that can influence actually this insulator metal transition of vanadium dioxide. Actually, the thing is that the vanadium oxide system is a bit complex system. As you can see here in the phase diagram, that is a bit complex. And also it can present various oxidation states with each oxidation state that have its own phase transition. So it can be a bit difficult to control this system because of the, as I say, of the various vanadium oxide phase that are often mixed. And then also we can have the effect of the grain size, the effect of residual stresses, and then the effect of doping. So here the idea is to all this actually will influence the electronic and optical properties of the material that we are going to make. And the idea is to focus on the effect of the doping. And then when we dope, actually our vanadium dioxide, what we do, we increase the concentration in carriers, in charge carriers. So we play with the electron-electron transition, and also we deform the crystalline lattice. So we play also with the electron lattice in interaction. And when we want to dope, we can use different strategy. For example, do the substitutional of vanadium atom, or the substitution of oxygen atom, or the interstitial doping. And all this, according to the strategy that we use, we can have different results in terms of temperature, transition temperature, or the transmittance that we get. And here, just to focus on two dopants that are mostly widely used in the literature, is there are tungsten and fluorine. Actually, tungsten, when we dope vanadium dioxide with tungsten, is that we have how to say, we decrease the temperature, the transition temperature, and then the limit is that we decrease also the transmittance that we don't want. But with the fluorine, we decrease. I will show here. With the fluorine, we decrease the temperature transition, and then we decrease also the transmittance. Not as much as in case of tungsten, but we decrease. But the limit, one of the limits of the fluorine is that it's also a bit dangerous gas, reactive gas. Most of the people in the literature use gas. And one of the alternatives can be the use of a solid target. So what we want to do then is to do the co-doping of magnesium with fluorine using a solid target, in order to take the synergy of both dopants, and we expect that it will decrease the transition temperature, and the transmittance will be much higher, because in magnesium, the effect of magnesium will maybe help to keep the transmittance higher. So one of the goals here is to do the synthesis of the vanadium dioxide doping with these two dopants. And how to elaborate that? We have three main stages. So the first one is to deposit our material using pulse laser deposition, or this will be done in laboratory Hubert Curien, and magnetron-sputtering in HF. And the second stage is to do the physical chemistry characterization. As I said before, it's a bit complex material, so it has to be characterized better to see what really we deposit. And then we do the optical characterization at the last stage. Just to highlight the insulator metal transition for pure vanadium dioxide that we have already started. Here we deposit our vanadium dioxide using PLD, and then we anneal at 500 degrees Celsius. We observe that. So we have a bit of mix of VO2 and V2O5 with the hysteresis that is a bit larger. So now when we anneal at 400 degrees Celsius, what will happen is that we have completely different hysteresis loop, as you can see here, and in Raman give us
Yannick,
that, yes.
Yannick, can you
yes.
please conclude within 2 minutes?
Yes, I have already finished.
Okay, thank you.
So the Raman give us that we have totally VO2, but in surface we have again another phase. Just to show you that we need to optimize the process of pure vanadium dioxide, and then go through the doped vanadium dioxide. So this is an application that we are targeting, is to do the thermally activated resonance grating using the vanadium dioxide. So since the time is going up, I will just say that we want to reproduce this device that has been already done on the lab, but using the doped vanadium dioxide. And to conclude, I will say for the achievement of this project, I have to be able to dope then the vanadium dioxide thin film using PLD and magnetron sputtering, do the physical chemistry and optical characterization of the film, and then design the thermally activated resonance grating using doped vanadium dioxide. And we also want to test this material in the integrating circuit for making random the infrared radiation blocking. Thank you for your attention.